one is about geometry. We start with polygons. What is a polygon? So a polygon is a closed figure with straight sides. So these are examples of polygons. And these are not polygons. Now, why? First of all, this isn't a closed figure. This isn't a closed figure either. And these have curved sides. Okay? I'm going to teach you something right here that may or may not be in the textbooks depending on which country you're from. But so we know that the three-sided one, polygon, is the triangle. And then there's the square and the rectangle. The family of polygons that have four sides, well, they're called the Quadrilaterals. Think of lateral as line and quad is four, so four lines connected together. Yeah. Then it goes on to pentagon. Penta is 5. Then it's hexagon. Hex is 6. Now, septagon would be next, but this has 8 sides, so this is octagon. Octa for 8. Octopus. Now, I'm going to list them out. So it's tri for triangle, and then it's quad. This is 3, 4, 5 is penta, and then it's hexa or, don't laugh guys, for 6. Okay guys, the second one is usually used for things such as trillion, quadrillion, pentillion, and sextillion. Yeah. Sept for 7, octo or octa for 8, usually in math it's A though. Nonagon for 9, and then deca or dec. Decagon for 10. Yeah. Eventually you're going to have to remember this for chemistry sometime in high school. Now, circle the polygons. Okay? So, first of all, which ones aren't polygons? We have a line over here that's not enclosed, so this one's not a polygon. And this one over here has curved sides, so it's not a polygon either. The rest of them have straight sides and are enclosed. So we circle the rest. Yay! We go down, classify each polygon. Well, to do that, we just count the number of sides, at least for now. There are specific types of polygons, say 4-sided polygons. You know that there's squares and rectangles and parallelograms. Remember, we learned this in grade 3. But right now, by classify, they mean quadrilateral. Just the blanket term for all polygons that have the same number of sides, or that specific amount of sides. Now, question number 4 has 1 side, 2 sides, 3 sides, 4 sides. These markings mean that if you have the same number of markings, then the length of the sides are the same, but if they're different, then the lengths are different. Now, 4 sides. What did I say 4 was? Quad. Quadrilaterals. This is a quadrilateral. Moving on to question number 5. We haven't really seen this one. So let's count the number of sides. 1, 2, 3, 4, 5, 6, 7. 7 sides. What's 7? Septa, or sept. So that's a septagon. And question number 6 has 1, 2, 3, 4, 5, 6 sides. Now, what's the word that we used for 6? Hex, or, well, the other one, but right now for geometry, it's hex. So, hexagon. Alright, that's it. Moving on to the next section, perimeter. Now, what is perimeter? Perimeter is basically the sum of all the side lengths in a shape. Think of it as you are installing a fence around a certain piece of land. The perimeter of that piece of land would be the length of all the fencing that you used. For example, here we have a triangle, and the perimeter would be the sum of all the side lengths. So what are the side lengths? 12, 13, and 5. We add those up, and we get 30 meters. So the perimeter is 30 meters, because 30 meters is the sum of 13, 5, and 12. What about for this lovely quadrilateral over here? By the way, this is a trapezoid. There's 7 meters, 7 meters, 6 meters, and 10 meters. You add these up, and you get 13 plus 7, which is 20, 20 plus 10, 30. Perimeter is 30 meters. Again. Oh, that's impressive. Now you may be asking me why there's just this uppercase P over there. Well, perimeter is usually represented by an uppercase P. For our practice problems, we have complete the sentences. The quadrilateral has, you don't actually need to count the sides here because it's a quadrilateral. Quadrilaterals have 4 sides. So the quadrilateral has 4 sides. To find the perimeter of the quadrilateral, to find the perimeter of any polygon, you add all the side lengths. Because there's plural. The lengths of its sides are, well, they're written right there. 6 meters, 15 meters, 6 meters again, and 15 meters. Find the perimeter. So we add them up. 6 meters plus 15 meters plus 6 meters plus 15 meters. And we end up with 42 meters. All right, that's a perimeter. So continuing to the last 3 questions of this section. Find the perimeter of each figure. Well, for question number 5, we have this strange figure. But no matter how strange this figure looks, it's still, well, how many sides does it have? 1, 2, 3, 4, 5. It's still a pentagon because it has 5 sides. It doesn't matter how weird it looks. Like, it doesn't look like the standard pentagon, but it's still a pentagon because it has 5 sides. But find the perimeter, what do? We add all the sides up. So there's 5 meters plus 6 meters plus 5 meters plus 9 meters plus 8 meters. Okay, that's all the side lengths. We add them up and we get, well then, 33. We get 33 meters. All right, moving on. Now question number 6. Remember those markings that I told you? Well, since the sides are all 5 centimeters, the markings are all going to be equal too. Anyhow, so 5 centimeters plus 5 centimeters plus 5 centimeters plus 5 centimeters. Sounds awfully like 4 times 5. 4 times 5 is equal to, come on guys, remember your multiplication table, 20. The perimeter, uppercase P for perimeter, is 20 centimeters. It's not going to magically change to inches, or meters, or feet. The units stay the same. I should probably put P over here too. Make sure it's an uppercase P though. This looks like some hybrid uppercase, lowercase p, but I mean, for the letter P, the uppercase and lowercaseness of it is really just a difference of placement. I mean, I guess usually the arch bit, the curved bit in a lowercase p is smaller, but okay, I'll stop. Moving on to the last question. We have a triangle. There's 3 sides. It's a triangle. We add up these 3 sides to find the perimeter because that's what we're supposed to do. 10 centimeters plus 10 centimeters plus 4 centimeters. 10 plus 10 equals to 20, and 20 plus 4 equals to 24. That leaves us with perimeter equals to 24 centimeters. All right, moving on to the next section, which is amazingly not actually problem solving. Area. The number of square units needed to cover a plane figure, which is a 2D figure, without overlapping is called area. For example, over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units, or 3 times 4 units. This is why multiplication is important, because when calculating area, a lot of times you would need to use multiplication. In fact, all the time. So this is 12 units squared. Of course, some teachers are picky and they will ask you to write out the entire thing because technically U isn't a measurement. Other teachers think that it's okay to write it this way. But here's the 3 different ways you can write it. 12u exponent 2, 12 units squared, 12 square units. Here, though, it's missing a chunk, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 12 minus 3. So this is 9. I'm just going to write it like this. Moving on to some practice problems, we have find the area of each figure. The rectangle has blah square units, while there's 4 units over here and 5 units over here. Now what does this look like? Suspiciously, it looks like multiplication. So 4 times 5 is equal to 20. The rectangle has 20 square units. The shaded figure has blah square units. Well, you see, the squares are shaded. And there's this hole in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 square units. Simple, right? It's just counting. It gets a lot harder when we stop doing rectangles, but hey, you're in grade 3. You don't have to worry about that yet. Find the area of each figure. So, I mean, this is a full square or rectangle. Is it a square or a rectangle? It's a square. And there's 6 on each side. 6 times 6, 36 square units. Or units squared. Here, it's another filled rectangle. So 1, 2, 3, 3 times 1, 2, 3, 4, 5, 6, 6. 3 times 6. That's 18. 18 square units. Oh, that one's missing something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 square units. Simple, right? It's mostly just counting, at least at this grade level. Moving on, some problem solving. Solve a simpler problem. A family of 2 adults and 5 children. That's a lot of kids. Each order a sandwich and a drink in the zoo cafeteria. Sandwiches cost $6 and drinks are $1. How much does it cost in all? So what do we know? We know the amount of people there are. And we know that each of them order 1 sandwich and 1 drink. Well, 1 sandwich and 1 drink, if you really want to be separate about it. And we also know the cost of the sandwiches and the drink. Note that this isn't the total cost. It means 1 sandwich costs how much and 1 drink costs how much. What do you need to know? The total cost for, it doesn't say if it's lunch or anything, for the family's food. Now here's how you solve a simpler problem. Basically, you go and you realize it's 7 people, and then it's sandwiches are 7 times 6, and drinks is, well, just 7 times 1. So 7 times 6 is 42. Drinks is 7 times 1, identity property, 7. Then you add them up, and you end up with $49. They spend $49. Yay! So, is the solution reasonable? Reread the problem. Does our answer make sense? I mean, our calculations make sense. But then again, we have to make sure our numbers are correct. 2 adults, 5 children, each order 1 sandwich and 1 drink. So yeah, that's 7 people. Sandwiches cost $6. We got that right. Drinks are $1. Okay. Our numbers are correct. What's the question? How much does it cost in all? So did we answer the question? Yes, we found the total cost. Does our answer make sense? I mean, our numbers are correct. None of the calculations are wrong, so yes, it makes mathematical sense. What other strategies could you use to solve the problem? Well, this is basically a multi-step problem anyways, so there really isn't that much of another strategy. Since solving a simpler problem isn't like drawing a picture, it's still just math. Now, solve. Use the solve a simpler problem strategy. The Smiths buy 2 adult tickets, or adults tickets, for $9 each, and 2 children's tickets for $4 each. How much money do they spend on tickets? Okay, so 2 adults tickets for $9 each, and 2 children's tickets for $4 each. 2 times 9 is equal to 18. 2 times 4 is equal to 8. 18 plus 8 is the total amount, and that's 26. They spend $26 on tickets. Okay, And our numbers are correct, our calculations are correct. Yeah, okay. We're fine. Olena buys 6 model airplanes for $8 each, 5 tubes of paint for $2 each, and 2 tubes of glue for $6 each. How much money does she spend in all? So that's 6 model airplanes for $8 each, 6 times 8, 5 tubes of paint for $2 each, 5 times 2, and 2 tubes of glue for $3 each. Okay? Our numbers are correct, right? Okay. 6 times 8, 48. 5 times 2, 10. 2 times 3, 6. You add them up. 48 plus 10 plus 6 equals to 64. Olena spends $64 in all. Check over your calculations, check over your numbers. Our numbers are correct, information is good. Our calculations are fine. We're good, we're fine. Our solution is correct. We also answered the question, of course, that's really important. Because you don't want to be asked, okay, how many oranges did Jones buy? And you don't want to answer something like, Kimberly ate 5 peaches. You get the idea. On to the next section. So, triangles. In triangles, there's 2 big ways to classify them. The first one is side length, and the second one is angles. Now, here are the 3 for side lengths. There's equilateral triangles, which means all 3 sides are equal. And these are the marks that you would use to show that they're equal. Now, in an isosceles triangle, isosceles, and yes, there's an S and a C. I cannot tell you how many times I've seen this spelled wrong, and how many times I probably spelled it wrong when I just learned this word. But this one is 2 of the sides are equal. So this one and this one are equal. Well, in this triangle, in this isosceles triangle, and this one isn't equal. Yes, guys, if the lines are of equal lengths, you use the same number of marks. If they're different, then you use different numbers of marks. In a scalene triangle, so scalene, we had 3 of them are equal, all sides are equal, 2 sides are equal, and because you can't really have one side is equal to itself, well, you can have that, but what's the point? Then, in a scalene triangle, no sides are equal. Pew, 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 pew. Actually, no. Yeah, the marks usually extend on both sides of the line. Anyhow, so that's the side length. Here are the angles. So first we'll have a right angle. Right angles are marked with this little square thingy. Now, right angles are usually what you use to build rooms because the corners are usually right angles. Now, of course, if you have a really weirdly shaped room, well, they might not be. But the corners of squares and rectangles are right angle. Rectangle, right angle. Wow, okay. Never actually noticed a similarity between those, but the words. Of course, I realized that the corners of rectangles are right angles. Somebody should make a tongue twister out of that. Right angles are 90 degrees, and on a side note though, you'll never find this. Well, you'll barely find this because usually that's just a straight line. Straight angles are 180 degrees. Okay, moving on, we have this. These are called acute angles. Now, it's literally spelled acute, except fused into one word. Anyhow, acute angles, well, they're smaller than right angles. So they're smaller than 90 degrees, but they're bigger than 0 degrees. Let's name this angle X. Yup. So this is how acute angles work. Anything that's smaller than a right angle and, well, isn't just straight up 0 is an acute angle. You can't actually really have an angle with 0 degrees because then that'd just be a straight line. And straight lines are usually 180 degrees. I mean, 0 degrees is theoretically possible in graphing maybe, but like, that's high school. Anyhow, the last type of angle is bigger. We're gonna name this X again because why not? Then 90 degrees. But it's smaller than 180 degrees. These are called obtuse angles. And yes, you can say that if somebody's obtuse, it technically also means that they're stupid. It's like calling someone dim. Yeah. Anyhow, so what does this have to do with triangles? If a triangle has one right angle, because triangles can only have one right angle, it is impossible for a triangle to have two. Because think about it, if a triangle has two right angles, well, how are you going to connect these two sides? Because this is the third side. Well, that doesn't work. And if you say that it's like this, well, it still doesn't work. And this also still doesn't work. So triangles can only have one right angle at most. If they have one right angle, then it's a right triangle. If they have one obtuse angles, because same logic, you can't have more than one in a triangle. If they have one obtuse angle, then they're an obtuse triangle. If they have all acute angles, if their angles are all nice and adorable, no, that's not the meaning. If they have all acute angles, then that means that they're an acute triangle. Okay? Some practice problems. Identify each triangle. So here, we have what seems to be a right angle. And are these sides the same length? Nope. So, yeah. 3 of the sides, well, they're all different length. And there's a right angle. So it's a right scalene triangle. The angle bit always comes first. obtuse scalene, right scalene, acute scalene, acute isosceles, right isosceles, obtuse isosceles, and oh, by the way, just that I tell you this, but this is supposed to be equilateral. And there's also a specific way to label angles. Equilateral triangles are always acute. Acute, equilateral. So most of the time, when you actually tell someone that it's an equilateral triangle, you don't need to tell them acute equilateral, because all equilateral triangles are acute. It's like saying all squares are rectangles, because that is true, fun fact. We'll be learning about that in the quadrilateral section. Oh, okay. And that's the next section. So here we have one obtuse angle. And then we have two unequal angles. How can we tell that? Because the lengths are unequal for the sides. And if the side lengths are unequal, the angles are also unequal. This is what you learn when you learn about triangles, guys. Here's how you label angles. It's still the number of marks. I know that I've drawn slightly out of the triangle, but hey, this is small, okay? Anyhow. So this is obtuse scalene. What about over here? Well, these two sides seem to be equal. And since two of the sides are equal, then that means these two angles are also equal, because that's just something that you learn about isosceles triangles. And there doesn't seem to be any obtuse angles. There also doesn't seem to be any right angles. And they all seem to be acute angles. So, it's an acute isosceles. Alright guys, time to get on to quadrilaterals like I promised you. Ay ay ay. Ay 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 ay. Anyhow, here's the thing. In grade 3, you learn how to classify quadrilaterals. Yes guys, quadrilaterals. Please don't spell it wrong. Using angles and sides. That's not the proper way to do it. After you learn about parallel lines, you start classifying with, well, parallel lines. A square has all sides equal for right angles, and if you were in a higher grade, you would also be told opposite sides parallel. Oh goodness, this is going to be crowded. Pretend there's a mark over there, okay? Pretend that this mark doesn't exist. And pretend that's a mark, okay? A rectangle has opposite sides equal for right angles. And if you were in a higher grade, opposite sides parallel. And for parallelograms, try to spell this, guys. It's also opposite sides equal opposite angles equal and opposite sides parallel. Now you may be asking me, wait, but that means that rectangles and squares are technically parallelograms. Yeah, this is true. Here's the thing. Squares are always rectangles. Rectangles are not always squares. Squares and rectangles, both, are always parallelograms. Except parallelograms are not always squares or rectangles. Yeah, there's also many other different types of quadrilaterals, such as the irregular ones that can't really be classified, rhombuses, and trapezoids. You'll learn that later. And by later, I mean grade 4. Identify each quadrilateral. Now, question number 1. The opposite sides are equal, and there's 4 right angles. So it would be a rectangle. It could also be a parallelogram. Because, hey, the opposite sides are equal and the opposite angles are also equal. Here, it's also 4 right angles and all the sides are equal. Well, more like except all the sides are equal. Technically, the opposite sides are still equal here. So specifically, this is a square, but technically it's also a rectangle, and it's also a parallelogram. This over here is the same case. It's a square, but it's also a rectangle, because squares are rectangles, and it's also a parallelogram, because squares are also parallelograms. Rectangles don't have to be squares, though. Parallelograms don't have to either. Now here, there's, well, no right angles. And when there's no right angles, it's not a square or a rectangle. But hey, the opposite sides are equal, and the opposite angles are equal, so it's a parallelogram. P-A-R-A-L-L-E-L, parallelogram. O and then gram. Continuing, it has 4 right angles and its opposite sides are equal in length. It is so 4 right angles. That's either a square or a rectangle. Maybe both, because squares, well, its opposite sides are equal in length. That usually means that it's a rectangle. Although technically, the opposite sides of a square are equal in length. Because if all your sides are equal, then the opposite sides are equal too. Yeah. Anyhow, problem solving. For this investigation, we're using the strategy of choosing the best strategy, which really isn't that much of a strategy. It's more of a go ham. Basically, do whatever you want. Charles decides to wallpaper a wall. I mean, it's wallpapering. What is he gonna wallpaper? The floor? I mean, hey, you could technically wallpaper the ceiling. Anyhow, moving on. Each patch of wallpaper is 1 meter by 1 meter. That's not that bad. The wall is 4 meters tall and 7 meters wide. how many pieces of wallpaper will Charles need if he wallpapers the entire wall? Now, I'm sure that I've taught you this trick when we were learning about area. If I didn't, then wow. Anyhow, but if you remember, you could technically, if something's 4 by 7, I'm not even going to finish drawing that. What does that sound like? Multiplication. Now what's 4 times 7? 28. So if it's 1 meter by 1 meter, then that's 1. 1 times 1 is 1. So 28 divided by 1, remember your division properties, is just 28. So Charles needs 28 pieces of wallpaper. He needs 28 pieces of wallpaper. Alright, look back at the problem to make sure our facts are good. Charles decides to wallpaper a wall. Each patch of wallpaper is 1 meter by 1 meter. The wall is 4 meters tall, 7 meters wide. How many pieces of wallpaper will Charles need if he wallpapers the entire wall? Check our calculations. 4 times 7 equals to 28. 28 divided by 1 equals to 28. Alright. Moving on to the next section. Section 8 is solid figures, which is really just 3D figures. The objects you see around you are solid figures, unless they're on a piece of paper. Then, well, they're kind of flat, which means that they're, well, 2D, which is not 3D. A solid or 3-dimensional figure is a figure that has length, width, and height. Those are the 3 dimensions: length, width, and height. 2-dimensional figures only have length and width. So these are the different types of solid figures that you are going to be learning in this grade. So there's the cylinder, which I'm sure you've seen somewhere. It has 2 circles, as technically they're both bases, the base and the top. And then it's the stuff surrounding the circle. Tubes are shaped as cylinders. Toilet paper rolls are shaped as cylinders. So these are cylinders. No, they're not spelled with S. Or just cylinder. That is, well, I'm sure you've seen boxes before. A rectangular prism. Now, what's this? Turn it upside down and you get a cone, because I'm sure you've all seen ice cream cones or snow cones. If you haven't eaten one of those ever, I'm sure you've still seen them somewhere. So this is a cone. And here, it's another type of have you seen a box thing, except you've also probably seen these as unit cubes. So it's a cube. And ice cubes, like the fancy ice cubes that are perfectly cubic. Yeah, well, you wonder why they're called ice cubes. And this, over here, is a square or quadrilateral, it might be a rectangle, based pyramid. But the big family of these type of shapes are called pyramids. I swear to my old math teachers, I have probably misspelled this more times than you guys have ever spelled this. Now, this is just the standard ball shape, like the tennis ball shape, basketball shape. Yeah, it's not called a ball though. It's called a sphere. So, the characteristics of all of these shapes, cylinders, well, it's just circle, circle, the stuff surrounding the two. Rectangular prisms, it's a prism that's made out of rectangles. So slap a bunch of rectangles together. Well, actually, no, it's not just random rectangles. But, well, they're rectangles joined together. All the sides are rectangles. Cones, well, it's a circle at the bottom and then this thing on top that makes it end in a point. So here's the thing. Here's the problem. Here's the big problem. Cones, if you ever tried to make a completely flat cone, like it stands up and the point is pointing directly at the ceiling, sky, wherever you are, it's actually pretty difficult. Anyhow, cubes, they're like rectangular prisms, except with only squares. Oh yes, and rectangular prisms, you can't have a square in them, or else they'll be called cuboids. But cubes, they're made out of 6 squares. Pyramids, the big family, it's triangles that are on a base that connect at a point. Here, that's either a rectangle or a really weirdly drawn square. It's probably a rectangle, though. Might be a square. Anyhow, so there's triangle-based pyramids, which have a triangle as a base and only 3 triangles that are pointing upwards. And there's square-based, which have a square as a base and 4 triangles. Rectangular-based, which is rectangle as a base, 4 triangles. There's also pentagon-based, hexagon-based, blah, 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 blah. But this is a general shape of pyramids. And then there's the spheres. Spheres are just round balls. So, nothing much. Identify each solid figure. Well, here, I'm not sure about you, but I sure as I am alive cannot see any squares in this. In fact, it's all rectangles. So what is it called when it's all rectangles? Rectangular that's an A. Prism. Here it's a circle and then something around the circle that ends in a point. And it also looks like an upside down ice cream cone, so it kind of looks like those in like stories where the ice cream cone falls on the ground and just splats. Actually, no, that also happens in real life. Never had it happen to me though. So I guess that's good for me. Anyhow, cone. Now this just looks like a toilet paper roll. Add another circle in the middle and you get toilet paper roll. But hey, what are these called? Circle as base, circle as top, the stuff surrounding it looks like a tube. Cylinder. And this has a shape as a base and triangles that are based on the base that point upwards and join at a point. So this is a pyramid. More specifically, I'm quite sure this particular one is a rectangular based pyramid. All right, moving on to some more good old solid figures. Except more. Complex solid figures are basically objects that have a mishmash of solid figures. Basically just more than one. For example, a pencil. A pencil has the cylinderish pencil part, and then the conical, yes, it's actually called conical, conical, except without the E, tipish bit. It's actually just a tip. Why am I calling it tipish? So this is the cylinder, and this is the cone. Now moving on, and identify each figure, well not each, identify the figures that make each complex solid. Well, we have a fire truck first. Okay, so the fire truck has this big rectangular prism over here. It also has this small one over here. It has another rectangular prism. So rectangular prism. And then it has the wheels, which are cylinders. Rectangular prisms, cylinders. And it really doesn't have anything else. It's just a bunch of rectangular prisms and a bunch of cylinders. What about an ice cream cone? When an ice cream cone has the cone, it's pretty obvious in the name, cone, and the scoop of ice cream, which is a circle, and that's a sphere. Because circles are 2D, two-dimensional, not three-dimensional. How do we make it three-dimensional with a sphere? Oh, that's a flagpole. That's a flagpole. That's one handsome flagpole right there. So it has the ball circle on top, and it actually has this little point on top too, so that could be a cone. And it has this little point, and then it has just this long cylinder. So there's cones, because there's 2 points. Sphere, because there's only one sphere. And cylinder. Okay, judging from the corner of the flag that I see right here, there's white, red, white, and blue. Okay, which of the flags that I know have white, red, white, blue? Oh, it's probably a Union Jack, as in the flag of Great Britain and Northern Ireland. The Kingdom of Great Britain and Northern Ireland, if I want to be specific. But hey, anyhow, moving on to volume. Alright, you know that there's, well, area, but there's also volume. Now, I know that area is a two-dimensional thing, which is you multiply the length and the width. Now, what's volume? It's a three-dimensional thing where you multiply all 3 dimensions. The length, width, and height. A cubic unit is a unit of volume. So basically, it's 1 unit as the height, 1 unit as the length, 1 unit as the width. Volume is a number of cubic units a solid figure holds. You can use cubes to help you find volume, and you can count the cubes, or you could just use multiplication if it's a regular shape like this. So it has 2 as the length, I guess, 3 as the width, and 2 as the height. So volume is really just length times width times height. Alright, this figure has a volume of 2 times 3 times 2, 2 times 3, 6, 6 times 2, 12. However, there are the ones that are not as regular. So for this one, you would usually just look at the regular part, which is the same as that. So this is 12. This is 12 already. And there's an extra 2. 1, 2. So 12 plus 2, 14. All right. let's go on and use the figure at the right to answer questions 1 to 5. The top layer has however many cubic units. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, and 1. So 6 times 6 is 36, times 1 is still 36. So the top layer has 36 cubic units. The middle layer has, well, it's the same thing, it's a regular shape. So it's still going to have 36. And the bottom layer has how many? It's still the same thing, so it's still going to have 36. How many cubes are there in all? 36 times 3, which admittedly you guys haven't really learned yet, so you'll just have to do addition. 36 plus 36 plus 36 equals to 108. The volume is 108 cubic units. Multiplication really comes in handy sometimes. Find the volume. Okay? So we have, okay. There's a deep groove over here. But there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 in one technically layer if you turn the shape around. And there's also going to be 15 in this layer here because it's the same shape. Plus 15. And there's also going to be 15 over here because, again, it's the same shape. So that's 3 15s. And for your information, 3 15s is equal to 45. Units cubed. This time, remember when I did units squared, it was a 2? This time it's a 3, because there's 2 dimensions here, but there's 3 dimensions here. Oh, here. There's 3 times 2 times 1. I wonder what that is. It's 6. 6 units cubed. Of course, some teachers, again, they don't like it when you write it like this because they say that U isn't the official thing for units, apparently. They'll tell you to write out the entire thing. You can say units cubed, or you could say cubic units. All right. That's it for this chapter. See you next chapter.